In this video, we're going to cover section 1.5.1 on zeroth order reactions. Now let's consider the following elementary reaction step where the reactant A decays, resulting in the formation of product P. If the reaction is zero order with respect to the concentration of A, then the corresponding rate law expression is as follows, where the rate of the overall reaction is simply equal to the rate constant K1. And we can see that if we were to raise the concentration of A to the zeroth order, this is simply goes to 1. And so the overall rate of the reaction is simply equal to the rate constant. Now the reaction can also be written in terms of the time derivative of A. So we can show the overall rate of the reaction is simply the consumption of A via the derivative, the change in the concentration of A with time. So as a result, we can equate this term with this term. And so the formation of A over time is equal to minus K1. Here we've just moved the negative sign from one side to the other. This is called a differential rate expression, and it relates the time derivative of A to the rate constant. It is also a standard differential equation that can be integrated as follows. So we have the change in A with the change in time, dA dt, equal to minus K1. If we take the dt, multiply both sides by that, we end up with the following, dA equals minus K1 dt. So if we integrate both sides, on the left, we integrate with respect to the concentration of A, from some initial concentration of A to some final concentration of A. And on the right-hand side, we differentiate the time from t equals 0 to some time t. In K1, the rate constant being a constant, we can take that in front of the integral. So if we integrate both sides, we end up with the following. We have A minus A naught equal to minus K1t. And so this becomes an expression that we can use to evaluate the kinetics of a reaction. So where the concentration of A is the concentration of reactant A, and A naught is the initial concentration of reactant A, K1, of course, is the rate constant for the reaction, and T is time. Thus, for a zeroth order reaction, the concentration of A will undergo a linear decay with time. And we can see that on the following slide. So for a zeroth order reaction, a good linear fit to the experimental data will be observed for a plot of the concentration of A against time, if there is a strong association between these two variables. The slope of the linear fit corresponds to minus K1, and the y-intercept corresponds to the initial concentration of A. It is important to note that the comparison of experimental data to an integrated rate law expression requires that the variation in concentration with time be accurately known over a wide range of reaction times to determine if the reaction indeed follows a certain order dependence. And so you can see in this particular figure that we would expect a linear decay of the reactant over time if it follows zero order kinetics. And this is quite typical of the dissolution of a solid in solution or some catalytic reactions where so long as there is some of that reactant present, you will see it decay slowly until it no longer exists. We also see in this figure, as the magnitude of the rate constant increases, the rate of decay of that reactant is going to occur much more quickly. Now, if only the reactant is present at t equals 0, the sum of the reactant and product concentrations at any time must be equal to the initial concentration of A. If we use this idea, the concentration of product with time for a zeroth order reaction can be written as follows. It's similar to a mass balance expression, where we have the initial concentration of A at any one point in time will be equal to the sum of the concentration of the reactant A and the concentration of the product P. If we rearrange this expression as shown, we can show that the product concentration is equal to A naught minus A, and then we can do a substitution for the concentration of A from our integrated rate law. What this provides us with is an equality that represents the product concentration in terms of the rate constant and the time at which the measurement is made. So for a zeroth order reaction, the concentration of product with time is independent of the concentration of the reactant, so long as some of that reactant remains. And we can calculate the product concentration at any point in time during the course of that reaction if we know both the rate constant and the time that we're interested in. Another characteristic of most integrated rate law expressions is something known as the half-life of the reaction. So the time it takes for the reactant concentration to decrease to 1/2 of its initial value is called the half-life of the reaction. And we denote that using the following symbol, T subscript 1/2. Now for a zeroth order reaction, we can determine what that half-life is equal to. And so if we start with our integrated rate law for a zero order expression, and into this expression, we substitute for the concentration of the reactant A with 1/2 A naught, which is the definition of a half-life. If we do this substitution, then our time becomes T1/2. And if we rearrange this expression for T1/2, we end up with the following equality. The half-life of a zero-order reaction is dependent upon the initial concentration of A, the reactant, divided by 2 times the rate constant. So as long as you know the initial concentration of A and the rate constant, you can calculate the half-life for that particular reaction, assuming zero-order kinetics. So if you have any questions about zeroth order reactions, by all means, send me an email. Thank you.